So the next section is on transformations of graphs, which is something that you won't do exactly this way in calculus, but understanding how numbers in the parent functions change the parent function is kind of beneficial. So I think it's just a nice skill to have. So what I'm going to do is we're going to go back and we're going to look at section C on page 5 and see those parent functions, and then we're going to do those transformations on the parent functions so that we can see how the graph has been changed. So for example 1, we're going to look at a square root graph. And so if you turn back to page 5 and if you look at the square root graph, you can see that there are some specific points on there that are not decimals that are kind of nice to look at. So 0, 0, 1, 1, and 4, 2 are pretty easy to graph, and they would be easier to transform than if you had one of these points that was like a decimal. So those are the points that I'm going to look at. And so I'm going to go ahead and write those down first. 0, 0, 1, 1, 4, 2. And then I consider the transformations that I can see in my equation. So any transformation that includes multiplying or dividing should happen first, and then transformations that include adding and subtracting can happen second. So here I have a number that's in front of the kind of like the inside of the function. I think of this as like the inside, and then this stuff is like the outside. So the very front has that 2, that's a vertical stretch. There's no number in front of the x on the inside, so that means there's no horizontal stretch or compression, but it does say -3, so that means it's shifted to the right 3. And then the +4 on the end means that it's shifted up 4. So the first transformation that I'm going to do to the points is that vertical stretch of 2. And since it's a vertical stretch, it means the graph is twice as tall, and that should happen to a y coordinate. So I'm going to take each of my y coordinates and multiply them by 2, which leaves me with 0, 0, 1, 2, and 4, 4. And then after that, I can go ahead and shift to the right 3 and up 4. So there's all the to the right 3's, and then up 4, up 4, up 4. And then if you have graph paper, you can get it out, or you can draw a little sketch or whatever. I have these nifty little sticky notes that have graphs on them. And that's what I'm going to do because I'm too lazy to go get another sheet of paper. Alright, so there we go. So you can see it looks a little bit taller than the parent function did, and it's definitely been shifted to the right enough. All right, example 2. Y equals -1/x plus 5 minus 3. So here, this is kind of an interesting parent function because it has some like weird points to plug in. You'll notice that I picked some examples that would be like the weird ones so that you guys know what to do with those. So with this one, what I typically do to transform this one is I would look at the horizontal asymptote and the vertical asymptote because on the parent graph those are at 0 and 0. And then for section C, I told you that the points that I would have plugged in would have been -2, -1, and -1/2. And then +1/2, +1, +2, but that's a lot of points to transform. And I think that after you've done the parent graph, you can kind of understand the way it works. So when we do the transformations on this one, I'm going to transform the two asymptotes, so the vertical asymptote and the horizontal asymptote, and then I'll just transform the points that had an x-coordinate of 1 and -1. So I'm going to think of our vertical asymptote, horizontal asymptote, and then -1, -1, +1, +1. And again, I'm just kind of looking back at my parent function for that rational or reciprocal function. And now I can go ahead and do what I did with the other one and think about these transformations. So I have a reflection over the x-axis, which means that something is going from like up here to down here, and so all the y-coordinates are going to change to the opposite sign. This is left 5 and down 3. So changing the y-coordinates to the opposite sign or multiplying the y-coordinate by a -1 is the only transformation that multiplies. So I'll do that first. So this is going to stay x equals 0 because that's like an x value. The negative version of 0 is still 0. And then I'll go ahead and say -1, +1, +1, -1. All right, and then I can do left 5, down 3. So left 5, ignore that one, left 5, and then down 3, down 3, down 3. And I'm going to draw this one on here so I don't have to grab another sticky. So vertical asymptote at -5, horizontal asymptote at -3. So -6, -2 puts this one right here. -4, -4 puts that one right there. And then you can see from those points that it's pretty clear like where the curves are supposed to be. And since we've drawn the parent graph, we kind of know what they should look like. But you can always, if you're ever unsure, you can always plug in more points and then transform them. All right, example 3. So for this one, I'm going to do y equals -ln of 3x minus 1. And again, you can kind of notice that I have not used a calculator for these because this is a scale that I want you to have. Obviously, I know you can just plug this into a calculator. However, basic knowledge of these functions and being able to do it by hand is really important. So if we look at this graph, then I have to think back to the stuff that we wrote on page 5 about the natural log graph. So we know that we can't plug in 0, we know that we can plug in 1, we can plug in e, and then we know we have that vertical asymptote of 0. So for this one, I'm going to say vertical asymptote of 0, I've got the point 1, 0, and I have the point E1. So if I look at these transformations, I have reflection over the x-axis. This is a horizontal compression, because anything that happens inside the function or inside the parentheses would be kind of the opposite of what you would think. So just like how this is left 5, that looks like a stretch, which means it's a compression. So horizontal compression by 1/3, and then down 1. So this negative and that horizontal compression are the two things that would multiply by the numbers, and then the down 1 would be adding or subtracting. So I'm going to do the reflection over the x-axis first. So that means that the y-coordinate is going to change to the opposite sign. So opposite sign of 0 is still 0. Opposite sign of 1 is -1. Should not have written the x's yet. All right, and then what we have to do next is take the x values and multiply them by 1/3, or you can divide them by 3. So 0 divided by 3 is still 0, 1 divided by 3 is 1/3, e divided by 3 is going to be e over 3. Since e is 2.7, that's a little bit less than 3, so a number that's a little bit less than 3 divided by 3 would be a little bit less than 1. So when we graph it, that's what we'll expect. I'm going to go ahead and get a new sticky so that I can graph this one. That's right, so why don't you pause the video so we don't have to wait for you? I don't know. That's no fun. Let's make the video longer. Alright, there's the sticky. So, vertical asymptote at 0. And then I have an x-intercept at 1/3, that's super tiny, and then a little bit less than 1, -1. So this little itty-bitty thing is what our graph would look like. And of course, just like I was saying before when we were like in the order of operations section, it's always good when you're practicing these by hand to plug it back into the calculator and make sure you got it right. I would do that, but I put my calculator away already. All right, example 4. So for this one, we have y equals 2e to the 2x plus 4 plus 5. I like really went to town on this one. Transformations. It's obnoxious. So for this one, we have a vertical stretch of 2, a horizontal compression of 1/2. I can't see how far left I need to go in the form it is right now because it's not factored, so I'm going to ignore that for a second. And then it has shifted up 5. I forgot to put our beginning information. So the E graphs are the inverses of the log graphs. So since I'm being lazy and I don't feel like referring to my packet, I'm going to trade the X's and Y's of everything because that's what an inverse is. So if I trade the X's and Y's here, then I know that my point is 0, 1 instead of 1, 0. If I trade the X and the Y here, I know that I have 1, E. And then instead of a vertical asymptote, it's going to have a horizontal asymptote. And if you want to look back at the section C to see if that makes sense, then you can do that. But this would be the points that we're going to start with. Okay, so now I'm going to think about this with that exponent being factored. So I can see I have a horizontal compression of 1/2, and then the graph shifts to the left 2. All right, so the two transformations we have that are going to require multiplication is that vertical stretch of 2 and that horizontal compression of 1/2. So I'll go ahead and do that vertical stretch first. This is a y value, so I'm going to multiply it by 2, and it's still 0. Multiply it by 2, multiply it by 2. And then with the x coordinates, I'm going to multiply those by 1/2. Okay. And now I can go ahead and shift to the left 2 and up 5. So left 2 is not going to affect that. Left 2, left 2. Oh gosh, 1/2 minus 2 is negative 1.5. And then up 5 would be 7. Up 5 would be 2e plus 7. Up 5 would be 5. Okay, so let me go ahead and graph that horizontal asymptote at 5. And then I have the point negative 2, 7, and then negative 1.5. And then I have to think about what 2e plus 7 would have been. This is definitely going to be off my graph. But 2e would be 2 times 2.7, which is, what, 5.4-ish? 5.4 plus 7 is 12 point something. So that's a little bit off the graph. That's not too bad. So that's up here somewhere. And then there we have our exponential graph. All by hand. Look at that. Don't you feel smart?